Am I audible?
Yes, sir, you are audible.
Sir. Yes, sir, audible, sir.
Hello?
Yes, sir, you are audible. Yes, sir.
Yeah, thank you. So, okay, the reason for changing the different parts of the access and the pole network is that the traffic demand in the worldwide traffic demand. So this particular picture shows the traffic requirement in the from 2014 to 19. From 2014 it was 2.5 exabytes. So currently it is 10 times more than that, around 25 exabytes. So, and particularly if in India, see, so number of subscribers is increasing from it was 10 years back, it was around 50 crores. Now it is around 120 crores. Nearly the entire population is kind of using the smartphones. And so both the rural and urban regions getting access to the network. So the traffic demand is obviously increasing year by year. So, who is actually controlling the development of these cellular systems from 1G to 5G? So there are two different organizations. One is ITU and another is 3GPP. It is a specialist agency of the United Nations. It is similar to the World Health Organization. So it was established in 1955. It's based in Geneva, Switzerland. There are around 193 countries are members of ITU. Around 900 business, academic, and different standard organizations are member of this ITU. For example, TSI is there standard development is 3GPP. It is a collaboration by around 7 regional telecommunication organizations from different countries. Major countries are like Japan, USA, China, Europe, India, and South Korea. So I mentioned in India, TSTSI is the standard development organization. So whatever the proposal you want technology improvement you have to make in the standard, you have to go through this TSTSI in India. Similarly, different Europe and the USA has their own organizations. So all these GSM, UMTS, LTE, and 5G are developed and maintained by these 3GPP. So the major contributors in these technologies many industry partners and also some academia. So this picture shows the IMT timeline. So basically, as I mentioned, the traffic demand is increasing. The ITU is studying this traffic trend and putting up some requirements every 5 or 10 years. So you could see by in 2000 before 2000 there was a plan for 3G. What should be the system design? Such things started in before 2000. That was happening for 12 years, around 12 years. And in 2000, it came into practice. Deployment of 3G started in 2000 and it went for almost 10 years. Then, from 2000 to 2003, we had a mission for IMT. It was put up by ITU. So it took some 9 years to finish the development of 4G. Then 2012 onwards, we started deploying 4G worldwide. And we see 5G. The actual 5G recommend was put up in 2015. The development happened for 5 years. So the last 5 years. Then currently we are in the state of deployment. So we could see 3G took around 12 years for development, 4G took 9 years, now 5G took 5 years. So it's the timeline for the time required for developing technology is reducing majorly. And also, whenever we develop the new technology, it also put up releases. 3GP put up releases, that is called release 13, 14, 15, and 16. So once they develop the technology, every year they will put up this new enhancements. Whenever possible, they will put up enhancements. Every year they release it. Whenever the new smartphone comes, those technology will be upgraded and you get the better performance. So as I mentioned, in 2015, ITU put up the requirements for IMT. So in 2020, we will be getting worldwide, we will be getting this much traffic demand. So we develop technology keeping in mind those requirements. So these are the major requirements. The downlink data rate by around 20 Gbps per base station. There can be many users that can connect to the network, but the base station should give 20 Gbps downlink throughput, and uplink peak data rate should be 10 Gbps. Each user should experience at least around 100 Mbps. Latency, the delay between the transmission reception should be around 4 milliseconds per video or audio applications, and 1 millisecond for URL LC. That is called ultra reliable low latency communication, where it is primarily for vehicle to vehicle communication or machine to machine communication, IoT networks. The latency for controlling the device should be around 20 milliseconds. Initial establishment such control information has to be done within 20 milliseconds. The connection density, it is expected that the connection density is 1 million devices per kilometer square. So if you see the 4G around 5 years back, the connection density was not that much, maybe around 1,000 devices per kilometer square. This is mainly because it was only smartphone used by human. Now, other than smartphone, there will be many new devices like vehicles and home equipments and industry tools will be connected to the base stations through the technology. So the number of devices will be increasing. So the reliability also, you might have experienced that inside your home, you may get poor signal performance and such things. In rural and village area, we get very poor throughput. So this can be avoided in 5G. That was the target in 2015. And bandwidth support also 100 megahertz. In 4G, we had around up to 20 megahertz bandwidth. So it was expected that we should support 100 megahertz from 2020 onwards. So as we have seen the previous one slide where we have mentioned about the core access network. So here you can see what are the different functionalities of core and access network. The access network, I mean the base station itself. The NG, that is called next generation RAN, where the base station handles all those wireless transmission, right? How much bandwidth will be used, how much resource will be given to the users, what should be the transmission power for each base station. That thing will be on the schedule. All those things will be covered by the base station. And the remaining functionalities like security, handover, mobility management, and those things will be internet access control. Those things will be handled by a core network. Where I mentioned AMF, UPS. AM is basically access mobility function. UPS is user plane function. SMS is session management function. So each call or video or internet browsing goes, or what kind of charging policy each one makes. For example, Geo will say 1 GB per day. Those things will be handled by the functions in the core network. So you could see compared to 2G and 3G and 4G, the G90 has more functionalities added into 5G. So we could see, so already we know about the 5G applications, right? We're going to switch off throughput and many. So here we can see some interesting applications practice. For example, it is used in automatic machines can uh, uh, do the milking by, but these kind of things require very low latency. The response time is much higher. So in the big farms, the automatic transportation and traffic management, such thing can be done. So already we know that in 4G itself changing the way we live, right? So there will be there is like a new and hello.
Sorry to disturb you, sir. Your voice is breaking, sir. Audio is not clear.
Okay, so now it's okay.
Now it's okay, sir.
Okay, so there are new services that are coming up. So we vehicle booking through travel is simplified. So these are changes due to happen due to it. The same thing is expected with 5G. The more devices will be connected and we get better services. So as I mentioned, ITU put up the requirements, and the 3GPP 3GPP came up with some technology improvement. So it proposed that we could get around 20 milliseconds. We could can be saved by 90%, and we could achieve 99% reliability. The number of devices can be connected much better. So am I audible?
Yes, sir. But in between, your voice is breaking, sir. Some continuity we are missing.
Yeah. Hello?
Yes, sir.
So it's okay?
Yes, sir. It's okay.
Okay. Yeah,
it's clear, sir.
Yeah. Thank you. So these are the new different enablers for 5G radio. The first thing is that the higher bandwidth support. You can support up to 100 megahertz bandwidth, carrier aggregation, small cells, massive MIMO, multiple antenna technology, flexible waveform design, then scalable frame structure, and the FEC, the forward data correction coding using LDPC. We had support start from 1.4. The frequency range also limited to 2.4 gigahertz. Up to 2.4 gigahertz only we had frequency bands for 4G. In 5G, both the bandwidth is increased, the frequency of operation also increased. In 5G, we have variable bandwidth from 5 to 100 megahertz at a time, and the frequency range also increased both at the sub 6 gigahertz and the millimeter frequency. So we are currently having 3.4 and 3.6 gigahertz frequency, and also millimeter frequency to 24 and 60 and around 70 megahertz as well. So these are the different bands used for 5G. We could they are named as N1, N2, and N3, and so on. So So similar to 4G, we had both the FDD and the TDD, frequency duplexing and time distance duplexing. So each band can give around 60 to 70, 60 to 100 megahertz of bandwidth. So these bands can be divided into small chunks and they can be used for by different operators. This is in the first one is showing the frequency one sub 6 gigahertz, and the another one is range. Example scenario. This is for 4G. In 4G, here we see N1, N2, N3, right? Similarly, 4G we had band 3, band 5, band 7, and band 40. But there are many bands like 1 to 3 was there, band 1, band 2, like that. But India majorly we are using band 3, band 5, 7, and 40. So this is the spectrum analysis output taken in our lab. We could see there's some peaks around from between 2.3 to 2.36 gigahertz. So we could see there are 4 different bands there. And so the first one and the last ones are with 10 megahertz bandwidth. The two are with 20 megahertz bandwidth. The same band, if the band is not used by 4G system in some certain locality, we could use it for 4G services. So in 4G it was, as mentioned, it is 20. In 5G, it can be 40, 60, or 100. In a single stitch, we can use the entire band for 5G. So in between, you could see there are some blank spaces. That is this called guard band. So to avoid this, we are using some guard bands. So this is one possibility of increasing the
Sir?
So these are the different frequency band used for 5G. I want to show you some example scenarios for 4G itself. In 4G, this is a snapshot taken in our lab from the spectrum analyzer, where you could see there are 4 different bands active in the band 40. From between 2.3 to 2.36, we have 4 active bands. So each one, the first one and the last one is having 10 megahertz of bandwidth. And so in between the bands, we could see some blank space, that is guard band. In 5G, this is 4G, right? In 4G, we have around 10 and 20 megahertz configuration. In 5G, it is possible to have 100 megahertz in stage. If you're using starting from 2.3, it will end at 2.4 gigahertz only. So this is another scenario with LD band 5, where you could see around 83 there is a transmission. This is the band used by Jio in India. So the low frequency band is giving better coverage. So Jio opted this particular band in throughout India. And next one is carrier aggregation. So apart from the higher bandwidth support, there is also a possibility to merge carrier frequencies from 2 different bands. There are 3 different configurations. One is called intra-band aggregation, within the band having some 60 to 100 megahertz. So each that 100 megahertz is divided into small chunks, right? 20, 40, 60. So the small chunks in different bands can be merged together to transmit data to the users. That is, the first technique is called intra-band aggregation and contiguous and non-contiguous. Like in the previous figure, we have seen. It can be merged from 2.3 to 2.33, or from around 2.3 and 2.34 as well. The first one, the first and second one be combined, or first and 3 or first and 4. So this possibility is there in carrier aggregation. So to get a higher throughput performance. Intra-band means we can merge the transmission from two different bands together overall. So here we have around 2.3 gigahertz, right? And we have around 883. So we can transmit both in those bands simultaneously to the users. So this aggregating the carrier boosts the throughput very significantly. And moreover, there is a spectrum utilization is better in 5G. In 4G, as I mentioned, if you have 100 megahertz bandwidth, so we can have up to 20 megahertz only. So there should be a guard interval also. If we neglect the guard band, so we could get around 90 megahertz, effectively 90 megahertz only utilized in the 100 megahertz. The remaining 10 megahertz is wasted. But in 5G, in instance, we can use at a stage 100 megahertz up to 98 megahertz is possible. So only 2 megahertz is underutilized. So this will be very beneficial for the operators because they are paying several thousands of crores for each 5 megahertz, 10 megahertz band. So this way, they could run the network with less cost, and they can give a lot of benefits to the users, end users. So the third approach is small cells. The concept of small cells came from the reason. So without the small, in 4G, let's assume that the macro basis. Macro means they have the coverage range from 200 to 500 meters. In such cases, there will be some poor performance on the cell edge. Between the cell edge, we could have poor performance. To avoid such effects, so some small base station can be deployed so that all users getting the proper throughput. In 4G, is kind of system is we get non-uniform throughput performance. In 5G, we will be getting uniform throughput. That means irrespective of the location of the users, all will be getting same performance. So I will tell you some example scenario what is happening in 4G. So this is the simulated result of SINR in a urban setup. That means very crowded city setup, where basically the center point is the base station, and there are here in this picture there are 1, 2, 3, 7 base stations are there. Each base station having 3 sectors. In the bottom you can see the antenna. This is a typical base station we see in any part of India. So we get 3 sectors. Each one is having 100-degree beam direction. So if we are very close to the base station, we get a very high SNR, that is around 20 dB. If you are away from the base station, we get around below 0 dB SNR. And in between the sectors also, we are not getting proper signal. This is the situation in 4G. If you put up the bases small cells in those low poor regions, the cell edge regions, we could get very high SNR, right? So the SNR can improve from 15 to 20 dB. Between then in all the issues will having the similar SNR range between maybe 10 to 20. So the low SNR region will be avoided. So that thing will happen in 5G. So this is the CDF of SINR for the slide we have seen. We have collected the SINRs and collected the CDF. We can see from this one, we can see what is the percentage of users having less than certain SNR. For example, if you take 0 dB SNR, around 7 to 8% of users having SNR below 0 dB. but 90% is having SNR below 0 dB. So from SNR we can get throughput, right? B log to 1 plus SNR. Let us assume that B is 5 MHz, SNR is minus 10 dB. So throughput will be 0.668 Mbps. So I have given some 5 MHz. Actually, when you schedule the users, it could be very less. Let's say in 1 MHz, the throughput will be even poorer. But if you use SNR 0 dB, it's improving 1.375. With 10 dB, we get 17.3. So with 20 dB, we have 33.3 Mbps. So you could, from this one, we could see that clearly. Based on the SNR, we can get the throughput. So some users are getting better throughput, some users are getting a poor throughput performance in the 4G system. What will happen in 4G is that the entire curve will shift towards right. I mean, the minimum SNR will be plus 10 dB and the highest SNR will be some 30 dB. So since the overall SNR is improving, all the users will be getting throughput around more than 17 Mbps with the considered scenario. That is how it will happen in 5G. So I want to tell you some useful tools so that you can see you can experience the real time performance of the 4G system. Currently, all are using smartphones and 4G systems are there. I want to show you how how we are getting this kind of performance in your system. So what you can do is that you just go find out any base station near your place and use these apps and go around the base station, very close to and away from the base station, and go take measurement in your home also. You could see variation in the both SNR, the signal strength and the throughput. So the first TRI My Speed app, it was developed by TRI and it was available free. Shadow Lab app is developed by us. Chandra Research Labs in Chennai. And there is another website called Collaborative Radio Frequency Observatory. So in Shadow Lab, you could when you press the new recording button, you could get the instantaneous RSRP. From this one, you can understand how the signal strength varies in your region. You can go to close to the base station, you get the RSRP around minus 70 dBm. That is the highest you can get, 60 or 70. But you go away from the base station, that is, we'll get around minus 130, minus 140. That leads to poor SNR as I mentioned. At the same time, we can also do the time-wise readings. By knowing these relative values, we could guess what could be the throughput we are getting, data rate we are getting. So for that, we can do another app. So try My Speed app that will tell you the location and corresponding downlink and upload speed as well. Also the RSRP. So you can take up measurement at different locations and you see the coverage performance in your region. So you could see that the service is not uniform in any region. So when 5G comes actually now 1 or 2 years, we could use the same applications and check the performance. We could get even uniform throughput anywhere in this in your locality. So CRFO is basically some collaborative platform for learning and contributing to wireless communication in India. It is developed by us. There is major applications of national level spectrum monitoring and dynamic spectrum access, current radio and applications. And also it can be used for machine learning tools. So here in the chat box, I'm sharing the link where you can see how to use this app and website. Yes. Okay, so you can use these 3 different tools to learn the concepts of 4G coverage and throughput, path loss, different factors of mobile communication. You can use these tools. So a detailed explanation given in the video I have shared in the chat box. You can go and check it. So this is the interface of CRFO. Different locations can be seen in the video. You can also see the different base station locations in your locality and how much bandwidth is utilized, what are the bands are used in your region. Those can be seen. This is a snapshot. You can see the coverage map or heat map. So the strength in your region. If you take the measurement from the MyTry app and put it up in the CRFO website, you can see this map. See, in 5G, there will be several deployment scenarios: urban micro, macro, indoor D2D services. In 4G also we had the same kind of system, but in 5G we have indoor and D2D vehicle-to-vehicle communication systems. The distance between the base station is around 200 meters in urban regions. In major cities like Chennai, Delhi, or Mumbai, we have a tight, very closely based base stations. In urban macro, the outskirts of suburban, outskirts of the city, we get around 500 meters. In rural region, we have 2 to 3 meters up to 5 kilometers as well. So we also have indoor base station in 5G. So there are two possible modes of connectivity in 5G. So the 5G enabled phone still can access the base station, but the control information goes through LTE core network. 1 second. So in many countries, the core network support is not established yet. For example, in India, even if the 5G is going to be deployed in this year, next year, it will take 2 to 3 years to get 5G service throughout India, because the core network part is not ready, because the fiber network has to be done. Unlike Europe and US, India is lagging in fiber optic deployment. So there is a project called BharatNet. So in even the rural regions, the government is deploying fiber cables. It will take few years, a few months from the first deployment in Chennai, major cities. So whenever the core network is not available, still the base station can be there, but the mobile can get access through base stations, but it will the connection information will be happen through the 4G core network. But in standalone mode, the call can go through both LTE and 5G core network and to the internet. So the fourth type of technique that boosts the 5G access network part is massive MIMO. Where in 4G we had around 8. In the initial release, we had around 4 or 8 antennas in the transmitter, and the receiver we had only 2 or 4 antennas. In 5G, this can be several folds. There could be 32 or 64 and 128 antennas. The current system supports 32 and 64 antennas. The main advantage of this massive MIMO is that it could increase the SINR condition. I mentioned that, right? In 4G we had poor SINRs and conditions. So those conditions, apart from deploying small cells, we can also improve the SINR by multiple number of antennas at the base station. Because this massive MIMO system can form a beam, so that the SINR at the cell edge of the users can be improved by several folds. And another aspect is spatial multiplexing, where multiple number of users can share the time and frequencies simultaneously. With the CISO, we could use hardly one user, but with massive MIMO, we can increase the number of simultaneous users in the system. So the capacity can be improved several folds. And also the range extensions. So when compared to single antenna, the coverage range can be increased several folds, and the energy consumption also very less with massive MIMO. And also the major complexity can be at the base station. So you could increase any number of antennas at the base station because the complexity can be higher. But you could still in the mobile station, mobile terminal, smartphones, we could use 1 or 2 or 4 antennas. That is sufficient enough because the base station takes care of all those signal processing stuffs. As I mentioned, it will give uniform service to all the users in the cell. In 4G, we had a different frame structure where the broadcast and the control information are transmitted for every 5 and 10 milliseconds interval. So continuously they have to be transmitted. But in 5G, there is a technique called beam sweeping, where since I told Massimo enabled the beams, so the beams can sweep from one direction, so that the users in those beams can be connected when the beam comes. This is the major difference in the frame. I mean, initial synchronization and broadcasting phase of the user requirement attachment process. So as mentioned, so the different base stations, they can coordinate together and serve multiple users without creating interference to them. This is a OFDM block where you could see frequency and time grid and the subcarrier spacing is there. So these blocks can be merged together, and on top of it, multiple users can be shared in the at the same time and the same frequency, but a different space domain. So without creating interference to the other users. So this is a summary of evolution of MIMO from LTE to 5G NR. In 2008, we had around 4x4 and 4x2 8RX configurations. Then slowly the number of antennas increased. Currently in 2018, we had around 32 transmit antennas at the base station. And the fifth enabler is channel coding. In 4G, we had turbo coding as the main coding technique for error correction and detection. LDPC is low density parity check matrix used in 5G system. So compared to 4G, the LDPC is capable of having better frame error rate, and it requires very low processing power. The gain is much higher in LDPC than 4G turbo coding. And moreover, the LDPC is suitable for sending large packets. If we are having data with several bytes, like 1,000 or 2,000 bits, this will be useful. But whenever actually for setting control channels, we need very few bits of data, very bits or bytes only. So up to 16. Suppose we want to send some control information to the mobile or from the mobile to the tower, we need very few bits. So in those cases, the LDPC may not perform better. So for that purpose, they are in 5G we are using polar code. So what is the advantage of LDPC? So this is the overall picture of all coding schemes. So we know that there is a Shannon bound, right? Shannon upper bound is there. B log to 1 plus SINR. For a given SINR, there is a maximum capacity that can be achieved with very low probability of error. So LDPC is very close to the Shannon bound. That is this is the best coding scheme that is available till now. So 5G adapted this LDPC, and we expect that the BLA performance is much better, and with very low processing power requirements. So another aspect is the energy saving system design in 5G. So whenever the one particular tower is switched on, it will always transmit some broadcast information towards the user terminals. This is for time and frequency synchronization and sending some useful information like location and operators data, such things. So whenever the mobile is switched on, it will actually go for cell search, right? So it will choose the best base station with a very good signal strength. That is called cell selection. Then the cell selection is done based on the cell specific reference signals. And then it will decode. Once the synchronization is done, time frequency is matched, and it will start to decode the information from the broadcast data. Then after decoding the information, it will ask for the connection to the internet and call and all. So we will explain this one in detail in the next slides. So as I mentioned, this is a frame structure where the broadcast information, if you think about the radio frame, it is 10 milliseconds. In 10 milliseconds, we will transmit the control information every 5 million, sorry, the synchronization and broadcast data every 5 milliseconds. So if the base station is on for 24 hours, the 24 hours the transmission will happen, keep on happening. Even the user is even not there, even night times, even there is no transmission, data transmission, this default information is being transmitted. This consumes a lot of power on the base station side. This is the example of our LTE base station from our lab setup. You could see there is a continuous transmission of data around 1 megahertz frequency. This continuous transmission consumes very huge amount of power. So that you could see there are some dots here. These are called cell reference signals. That is for used for finding out the signal strength. So each base station will transmit these cell reference signals. The user equipment will find out the strength, compare the strength, and attach to the strongest base station, right? For that, this is used. So we could see the whole time frequency grid. There is a continuous transmission, even though there is no data transmission, even though the mobile is unconnected. This is a summary in this one. In 4G, as I mentioned, every 5 milliseconds there is a synchronization signal. Every 10 milliseconds, red lines, that is the broadcast signal, and some dots are cell reference signals. This is entirely avoided in 5G, where the frame duration is changed to 20 milliseconds. The frequency of transmission is reduced, the energy is optimally saved. The cell reference signals concept also changed. As I mentioned earlier, beam sweeping, there instead of sending a cell reference signal, the beam sweeping is done. And that is also around every 20 millisecond interval. So this, if you consider the total base station power consumption, the circuit power default, whenever the tower is on, that there will be default power circuit consumption. And whenever there is a data transmission, that B data will be there. Then control information, synchronization, broadcast, and the CRS. So the major part of energy is consumed in 4G due to the synchronization, broadcast, and the CRS channels. So these throughout the day, if you see, the P data only going to change according to the user traffic. So in the night time, the P data will be, let's say, 0. Then there is no user is active, P data is 0. Still, the remaining part will be active in 4G. But in 5G, since these remaining terms are reduced significantly, we could get around 70% energy saving. So the operator who is running the network, he could save a lot of money, and that benefit at the end will go to the end users only. So I want to discuss about this multipath threading concept a little bit. That I will explain why the 5G adopted a flexible frame structure. So we know that all of you know that there's multipath threading in mobile communication, where the signal propagates. When the signal propagates, it travels through different paths and coming to the user terminal. That is having different power delay profile. If you send a single pulse, there will be multiple subpaths will come, and will get some power delay profile like this. To avoid intercell interference, in OFDM we are dividing the entire bandwidth into small chunks. This is called subcarrier, small subcarriers, so that the equalization can be performed much better way. Actually, this particular power delay profile will be different in different scenarios. For example, if you go to rural side, or if you are within the building, and if you are going on the traveling on the road or in a street, in each scenario will be different, right? We are having tree somewhere, there will be a building somewhere, so it need not be same. It will be different entirely. So in 4G we have fixed, assume that there is a fixed symbol duration according to this design. In 5G, we adopted a flexible design, so that different configuration can be used for in different scenarios. So this is a snapshot from the Rappaport wireless communication and practice book, principle and practice book. You could see the RMS delay spread is different in different regions. In suburban, urban, indoor situations, it varies from few tens of nanoseconds to several hundreds of nanoseconds. So, but in 4G we are using, when adapting to the variations in the environment, we are fixing the one. So so we are not using the advantage of having flexibility in the decision design. In 5G, it is there. For example, the symbol duration basically roughly designed based on the RMS delay spread. The symbol duration should be at least 10 times greater than the RMS delay spread. So you can see that there is a delay, right? It should be, the symbol duration should be at least 10 times greater than that, so that we get better performance in the system. The subcarrier spacing also related to that symbol duration. So this is the time frequency grid, right? So in LTE we have this information is transmitted for every 1 millisecond. That is called a subframe. The subband is called in subband is 180 kilohertz. I mean, in 180 kilohertz there is 15 kilohertz of subcarriers are there. So this is that is called a physical resource block in LTE. This is always fixed. Whether you are traveling in a train or home or street or road, in rural side, urban side, it will be fixed. But in 5G, this is changing according to the scenario. For example, as I mentioned, the outdoor and macro regions, the delay we are getting, it's going to be huge, because the distance travel, the signal travels is huge, large, right? So accordingly, according to this previous formula here, the T is also higher. Since the subcarrier spacing is inversely opposed to the symbol duration, we get very narrow bandwidth, a very narrow subcarrier spacing. But in some, for example, in indoor scenario, the symbol duration can be short. So in that case, we could use a wider band. Even in the millimeter wave, this can be much better. So we could use around 120 kilohertz of bandwidth. So according to the scenario, like indoor, outdoor, or the frequency range of operation, and I also forgot to mention that the power delay profile that you're getting, that depends on many factors, right? Frequency, environment, the building structure, components used, material used in the building, all those things. So the 3G organization has taken many different several measurements and came up with some empirical models to find out those exact RMS delay spread. Accordingly, they have designed this subcarrier spacing and such things. So this flexibility enables to adapt the symbol duration in some applications. For example, in vehicle to vehicle communication, the latency is very less. Requirement is very high. That means it should be the information should be sent within a few milliseconds or 1 millisecond, something like that. So in those situations, we could get different slot data as well. I will explain it a bit later. So this particular table shows the bandwidth configuration from 5 to 100 megahertz, the corresponding 5 sub-carrier spacing. Then for this configuration, how many physical resource blocks are there in the system? So it is varying from 25 to 273 in different combinations. And the symbol duration also varying according to situation. As I mentioned, in the second table, you can see that slot duration is 500 microseconds, 250 megaseconds, 120 megaseconds, depending on the sub-carrier spacing. In these situations, so whenever you are going for watching some YouTube video and those things, delay is not that much significant. You can tolerate a few seconds of delay as well. But in some applications that requires very low latency, like autonomous driving or industry automation, we need very few use the symbol duration, large symbol duration. We have to go for very short. So in those situations, even 0.25 milliseconds is also possible. So that is reflected in this figure. We could see that slot duration. So the low latency applications, we can use low latency and small coverage. Indoor scenarios, we could use even 0.0625 milliseconds duration. In outdoor large coverage areas, we could go for 15 kilohertz and 1 millisecond slot duration. So this is the flexibility of in the 5G system. Again, each slot is again divided into small sub blocks, that is called a symbol. Basically, depending on the situation, we have cyclic prefix duration as well. That is also variable in some scenarios. So finally, we have discussed different techniques that enhance the 5G system performance. Right, one is higher bandwidth, carrier aggregation, and the beamforming, and yeah, these are the major things, and the flexibility is frame duration, such things. So this particular formula is useful for calculating the data rate by 5G base stations. So there is summation here. This very J1 to J. Basically, this is carrier aggregation. This is due to carrier aggregation. So I mean, J, we can get up to, I think, 8 different bands. If J means 1 means N1 band, 2 means N2 band. So the bandwidth from particular band can be different bands can be added together and transmitted, right? So the combination gives this summary summation symbol here. So NBW or PRB, that gives the number of physical resource blocks available in each band. So if you are using 5 different, suppose let's assume that N1, N2, N3, N4, N5, in each band we are using 10 megahertz. That summary will give the 50 megahertz total, or we can use combination of 5, 10, such things. So accordingly, we have to feed this information here. The V layers related to the number of MIMO layers, that is up to 8, vary from 1 to 8. The RMAX related to the maximum coding, possible coding rate. Q is the modulation order. In 5G, we can go up to 256 QAM, so it is 8, maximum is 8. And there is a different factors that varies the symbol duration. The TS mu is basically average symbol duration that reflects in the throughput calculation. There is additional overhead and all. So this particular expression is available in many internet and in many textbooks. We could use it and understand what it is, each terminologies. So here is some example table I have given for varying number of LIS and bandwidth. If we vary the LIS from 1 to 8 and bandwidth from 5 to 100, we could get up to 4.67 Gbps of data rate. With this, we consider single beam. If you serve one user simultaneously. But if you go for 8 beams, I mean, like especially differentiating users, then you could get up to 37 GBs of data rate. So I have given a link at the bottom. You could go there and check it with the different possibilities. You could see what are the possible throughput performance in 5G. So another aspect I want to cover is the narrowband IoT. IoT is having a lot of new applications, right? As I mentioned, other than the mobile phone, there will be a lot, many new devices are coming up. And that is mainly for smart home automation, farming, smart transportation, smart city concept is coming up, smart healthcare, and those things. There are different IoT applications. Compared to usual mobile traffic, that the traffic characteristics of IoT is generally different because they need not transmit information very frequently. So they can transmit the information every minute or hour basis or even day basis applications. The data rate application requirement also not huge, but several tens of kbps, sometimes some 100 kbps. And the battery life also important. So they can be active for a very short time. And yeah, this is a summary of different IoT technologies. You can see that the range and data rate requirement is varying in different situations. So these technologies basically used for different services. So now narrowband IoT is a concept that even the cellular towers can give service to the IoT nodes. Main reason is that the range can be extended, right? In all those previous technologies, Zigbee and such things, the coverage is range is limited, right? With 5G enabled system, we could get a very large coverage range. You could see in the NB IoT around 10 to 15 kilometers of coverage, 2 TB of data rate, and the lifetime also 10 plus years. The battery you have to change, no? So that is every 10 years you need to change. So the requirements are like this. So it should be low cost, low power consumption, long battery duration. And so I mentioned the low throughput, but since we will be having several millions of devices, the aggregated throughput will be very high. So we have to find out the way to manage this different kind of traffic. This is for example scenario where for example, if you are watching a YouTube video, basically there is a mistake in the table. Its last column should be data consumed per hour, I think. Yeah. So if you go for 144 low resolution video, we get around 3090 MP. But if you are watching 1080 pixel video, the consumption is around 2.2 to 4.1 GB. So this is, we can see that relatively, this is a huge data traffic, right? But in IoT, it is different. It's much less, but the traffic, everything is characteristic is different. So there are different modes of deployment in IoT. So the bandwidth used for IoT transmission is around 200 kilohertz only, not like several megahertz in for typical mobile users. If you consider single 18 megahertz bandwidth, we have seen that several subcarriers and bands, right, within small chunks. So you can dedicate the subcarrier bandwidth for the IoT within this band itself. That is called in-band operation. There's another possibility. We have seen the several blocks, right? So within the guard bands also we can put the IoT transmission band, so that they won't interfere with the existing mobile traffic users. This is the example I have shown earlier. This is, for example, LTE system. Same thing can be used for 5G also. So we could see that there is a gap between these bands, right? So those bands can be used for IoT. Since it is 200 kilohertz only, this can be used in between, like these here and these places. Within the band also we can use, that is called in-band operation. Another approach is we could use GSM bands, because in GSM we have very large number of unused bands, because nowadays we are started using smartphones, all are using smartphones. So all those phones are connected to your 4G base station, right? So now the 2G base station bands are becoming empty. If you see, if you observe the active frequencies in 2G bands, you could get roughly or only 10 to 20% of frequencies are active. The IoT is more suitable in this frequency range because it is having 200 kilohertz, right? GSM also having 200 kilohertz of bandwidth. So there are 124 channels in EGSM Android band, where the downlink frequency is around 930, varying from 930 to 935 to 960 megahertz. Within that 25 megahertz, there are 125 channels with the 200 kilohertz of bandwidth. So this IoT can be the transmission can happen in that frequency range. So that's it. Here I am ending my presentation. So if you have questions, you could ask. So as I mentioned earlier in this particular slide, you could use these 3 different apps to know about different terminologies. You heard about the path loss, shadow fading, and small scale fading, right? So all those things can be understood by taking some measurements simply using your smartphone. We have to use these 3 different tools to understand how the coverage and the throughput performance works in a typical cellular network. So in the next session, I will also discuss about the test bed we have developed. We will having some better understanding of the whole system behavior in 4G and 5G.
Okay, sir. Thank you.
Yeah.
Participants, do you have any queries? Unmute
Hello,
your-
sir.
Yes.
Hello. Good afternoon, sir. Sir, the carrier aggregation of different bands are done. This is to save the bandwidth, or means that term you are used, no, carrier aggregation.
Yeah. So
Sir.
Not to save the bandwidth, basically to increase the bandwidth support. For example, the reason is that suppose if you are having such a typical cell, sometime what happens, the particular cell may be located some very hotspot, right? Some very crowded market area. There are many users are there, so that cells will be crowded, right? So the bandwidth may not be enough to support the users. So in the situations, there may be another band available far away. Those bands are a bit empty, right? So those bands can be aggregated together to use a better throughput to the other users.
Okay, like sports where the online is going on, there it can be supported with carrier aggregation support.
Yeah, not only that scenario. So because whenever the FCC or ITU is assigning the bands, it's already allocated 5 small chunks, 5, 10, 15 like that. So it was like it was 10, 20 years back. It was assigned. I mean the radio spectrum was scheduled like that. So operators also bought the spectrum like that. So your mobile phones also designed according to that, right? So we cannot change the frequency bands, right? So another approach is that we can use the signal processing technology in your phone, RF technology, so that the bands can be aggregated. That is the main reason we are doing the aggregation.
Okay, sir. Okay, thank you, sir.
Yeah.
Sir, another question is, sir, while when the users are far away from the base station, the different routes are traveled for different path, multi-path, you said, sir. The different packet reaches different destination with a different time slot. Again, there may be a problem of synchronization of the packets in the receiver side.
Can I repeat the question?
Sir, base station is far away from the user. That time, the multi-path, due to the
Yes.
multi-path scenario, users' packets are reached destination with a different time slots. But in the user side, there may be a problem of synchronization at such, because many critical routing paths are followed.
No. Yes. So what I mentioned that the system design, 3GP taken care of that. So before designing the system itself, the business symbol is such that it 10 times greater than that symbol duration, right? It's not a packet delay. It's a simple signal delay. So when you transmit a single pulse, it may reach after a few milliseconds. Sorry, few nanoseconds, not in milliseconds. So your slot is in milliseconds, right?
Sir. Yes, sir.
Yeah, your slots are in millisecond basis, but the delay I'm talking about, the signal propagation delay, that is in nanoseconds. So that could vary from few tens of nanoseconds to some hundreds nanoseconds. So in the system design, that has been taken care of, but in LTE that was fixed. So due to this particular, hello.
Yes.
Hello, sir.
Yeah, due to this particular, if you fix this such things, suppose if you are inside a home, right? Inside the home, you are getting the delay on the propagation delay around, let's say 10 nanoseconds. If you are on the street, if you are traveling in the road, we get around 100 nanoseconds, right? So the symbol you designed is kind of 10 times higher when you are inside the home. So it's kind of, you are losing the bandwidth somehow. So in OFDM, right, these things are interrelated. So if you are using the increased large symbol duration, we are losing the band
Some bandwidth is lost.
Yeah, or also related to this what you call the error rate also more. The signal will fluctuate much faster. Inside outside if you are outside the home, the fluctuation will be much faster. But inside the home, since you are stable, right, fluctuation is not that much. It kind of always constant propagation characteristics in your home. So the system you designed for outdoor, if you use that for indoor, we are losing some aspects of the in terms of throughput or energy stuff like that. So that is avoided in 5G. So that suppose what I mean that if you are roaming around outside outside, right, outdoor, so that time you will use macro tower. When you are inside home, you will use a small tower, small base station. That is different configuration. Yeah.
Okay, sir. Thank you, sir. Sir, then WiMAX and LTE features are means WiMAX is outdated now. LTE will dominate WiMAX.
Yeah, no, actually, I mentioned right. IT is the body that put up the requirements. So there are different organizations, they can collaborate together and come up with the idea. So WiMAX is the different set of organization, 3GP is the another set of organization, right? So 3GP belongs to Europe, WiMAX belongs to US. I mean, some companies located in Europe, they combine together and come with 3GP ideas. And another group is called 3GP, I forgot the exact name. Another group that is from US based. So due to this competition, huge support came for Europe-based companies. So that is 3GP. So in the competition, 3GP won, WiMAX lost. That's it.
Okay.
So I mean, whenever the IT put up the requirement, different entities can come with the idea. This is basically competition only. So whoever is having more money and political influence, right? They can. So now currently the entire mobile communication is dominated by the Europe. So European community. US is having less influence on this telecommunication part. Now China also coming up. So WiMAX is not being used practically. So we are throughout the world all adopted LTE and 5G only, 3GP standards.
Thank you, sir.
Yeah, welcome. So any other questions?
Any more questions from participants? Okay, sir. Thank you very much, sir, for your informative session. So participants, again, we will meet at 2 o'clock, demonstration on 4G, 5G test beds by Prabhu Chandra, sir. Okay. Thank you, sir.
Thank you.
Thank you so much, sir. Nice presentation, sir. Thank you.